thanks a lot for the invitation. It's very nice to be here. Last time I came, I think it was many, many years ago, and I got lost on campus yesterday. So apparently I didn't remember that much, the topology here. So I would like to talk about like some kind of interesting, well, from my point of view at least, geometric problem involving mainly harmonic maps and harmonic mappings, and some kind of variations of these when looking at liquid crystal flows. So the thing that I want to understand is how the dichotomy between regularity and singularity formation. So let me start by a very incomplete slide on harmonic maps. So let's take two closed Riemannian manifolds, and M and N. So I will call very often M the domain and N the target. And I consider the Dirichlet energy defined in the usual way. And I'm asking myself, so the map U is from M into N, and N is isometrically embedded into an Euclidean space by Nash. And basically, this type of map is some sort of generalization, a nonlinear version of harmonic functions, if you want. And what I want to understand is the existence and the critical, the existence and the regularity of critical points in general of this energy. And so if I do like a classical first variation, I end up with this equation 1, which is the equation of harmonic mappings. And the gamma is the second fundamental form of the embedding. So it's a very simple equation, and even when the target is a sphere with a round metric, it's even simpler. That is the next slide, but which has attracted a lot of works. And I just here quoting some names, but actually, like, I have to apologize because it doesn't give any kind of enough credit to all the people who worked on it from many different aspects. And let me explain you.
Samson might be mentioned since they started the.
Yes, that's correct. It's the next slide after. Yeah. So So basically, let me take the target to be sphere, the Euclidean sphere, and this equation that I just wrote 1 here becomes this very simple equation here. And so the parametrization is modulus of u squared equal to 1, right? The target is a sphere. And you can see very quickly that at the level, even at the level of regularity, imagine that you take for the domain, a bounded domain, and you put a nice Dirichlet data, and you solve by direct method of calculus of variation, by minimization, right? Let's say. Then you get a solution, you can construct a weak solution of this equation, but you figure very quickly that the right-hand side, because of the square of the gradient, is L1. Right? So you are borderline automatically for regularity, and it happens that even in 2 dimensions, in 1 dimension, when the domain is 1-dimensional, this is a geodesic equation, but in 2 dimensions, even in 2 dimensions, the situation becomes complicated. And so existence is an issue, particularly if you are not considering a Dirichlet problem, okay? If you are in the general setting of a domain being a closed manifold, so it's not a Dirichlet problem. I will come back to existence in a minute. But the regularity as well, and all the people that I quoted in the previous slide actually worked under different assumptions on regularity, and one had to wait to Hélin in the mid-90s, who proved that, any harmonic map from a Riemannian surface into any smooth target, compact smooth target, not only spheres, is actually smooth everywhere. And the reason why is that this result is not trivial is because actually what Hélin managed to exhibit is a difficult structure on the right-hand side, gradient u square u. So there is an algebraic cancellation which allows you to use in 2 dimensions. You prove that not in 2 dimensions, well, in any dimension actually, you can prove that gradient Q square U is in the Hardy space, so it's better than L1. And in dimension 2, if the Laplacian is in Hardy, you are in continuous, and it's enough to bootstrap and get regularity. Well, but the thing is that in 3D, okay, so a map from the 3 ball into the 2 sphere, Rivière constructed, like in the late 90s, a weak harmonic map which is discontinuous everywhere. So the best you can hope in higher dimension is having partial regularity in general. So you're going to be smooth outside of a small set. And the question is, how bad or how good is this singular set?
So the target is just a standard sphere. And
Yes.
Otherwise, the equation doesn't make sense, right?
Yeah. This is a standard. Yeah, of course. This is a standard. Yeah.
So maybe this is the place where it's important that the sign of the Laplacian is the classical one, not the modern one, right? Okay,
so I'm French, so for me Laplacian comes always with a minus, and I'm not a geometer, so it's even another reason to put the minus. Okay, so Lyons was always putting the minus for weak solutions, and so I'm French and a PD person, so I'm accumulating. So that's why there is a minus, but it is important, yes. So basically the whole point of many works related, and actually with application in geometry it's not a technical, it's not only a nice mathematical issue to understand the regularity of those maps. If you want to do geometry and use this map to prove rigidity result, you need to know where and how they are singular. So my talk will be mainly at the parabolic level, so I will come very quickly to the heat flow of those maps, but the interplay between regularity and this singular set. Okay? So I left another work, the existence issue, and let me mention. So to build the first example of those maps, come back to a paper of the mid-50s at the Hopkins journal, at the American Journal of Math, by Hills and Sampson, where so this is the first paper I know by mathematicians where they used the gradient flow to solve an elliptic equation. And it's the mid-50s, so very likely the physicists knew how to do it, but this is the first paper I know where it's done this way. Usually it doesn't go this way from parabolic to elliptic. So basically you run the heat equation, you run the heat flow, and you hope that at least you have like a nice solution all the way to plus infinity, converging to a stationary solution of your problem. And this is exactly what Hills and Sampson proved whenever the target is sufficiently negatively curved. Okay, and then they proved that you have a unique global solution, which is happens to be smooth by some sort of a priori Lipschitz bound. And so basically, of course, already it doesn't apply for my result here when I take the sphere. Okay, I cannot use this argument, well, at least directly like this. And you can relax the negative curvature of the target a little bit, but this is basically just technical somehow. And what happens when you are positively curved, where a very famous paper of Chang, Ding, and Ye proved that you have finite time blow up. Okay, so basically the picture is the following. Well, I mean, if I can draw something, so what you can prove by partial regularity is that when you evolve in time, you're going to blow up at a finite number. So here, this is 2D, okay? This is my space-time. You start with a nice initial data, okay? And you're going to blow up at finitely many time, okay? It's very important, like there is finitely many of them, and possibly even at infinite time. Okay, whenever the target is positively curved, think about the sphere, and at each blow-up time, you blow up in space at a finite number of points. Okay?
So, sorry, if the equation blew up at time t, how do you define the equation after that?
You can restart the flow because you have control of some local, I mean, you can design a notion of weak solution to restart the flow. You can push the flow. And it's very important that you have, it's like in Ricci flow. It's very important that you have finitely many of them, of course, which doesn't happen in higher dimension in general.
Oh, so if we give in the finite energy for initial data, so that means we can control how many blow up?
Yes, I will come to that in a minute in the blow-up analysis, and you will understand how I can restart the flow. So you can but basically the picture is that, which is already bad because if you remember this equation, all the weak solutions are smooth, okay? The stationary equation, and if I put like a dtu, well, I already produce very easily non-smooth solutions, okay? So to come to this singularity analysis, one of the questions you can ask is that if I blow up, how do I blow up? And it's important to continue my weak solution, right? Well, if I blow up by bubbling, so by geometric bubbling, so I will extract like an entire solution of my stationary equation, okay? So in some sense that, if I assume capital T to be the first time I blow up, that could be infinity, by the way, also. Okay, so of course I cannot blow up at the level of U because that satisfies my constraint equal to 1, so I have to blow up at the level of the gradient. And by a series of works of many people, you can, along the subsequence, you have a soliton resolution. Okay, so you converge to a body map U star, which is H1 which is H1 in the domain, and you blow up with K spikes in the domain. Okay, so this is the domain. Think about the disk. I will blow up at K finite K points in my domain, right? And at each of these points, okay, Qi, I rescale in lambda I, right? I modulate, and I extract one bubble, so an harmonic map from R2 into S2, okay? From it's called an harmonic sphere. And so basically, another way to say this type of thing, so this is the way you will push the flow, right? Because you know how the contribution to singularity, these are bubbles, okay? So if you blow up at one bubble, you remove it and you start the flow again. Okay, so this is one way. There is another way. There's one way to build, to continue a weak solution after singularity.
But you get a continuous solution on a puncture domain.
Yes.
A number of punctures.
Yeah, a finite number of punctures. Yeah, yeah. If you have lines, which is happening in high dimensions, then the situation becomes drastically, of course.
There are some singularity removable results. That means if we blow up, but the function is smooth.
There is a singularity, there is a removable singularity level result of Bullenbeck at the level of the stationary. Yeah. And another way to say, to formalize this picture, right? This is, well, okay, let me comment that. Is saying that the gradient concentrates as measures, right? This is exactly that, okay? Well,
so it's playing a role that there's a role of conformal invariance.
Let me come to that. Of course, like it cannot, if I'm super critical, so I break the conformal invariance. This is because this very nice picture is only in 2 dimensions because my initial energy is conformally invariant, here, in 2 dimensions. And it's very important to have this bubble, this profile decomposition. This is this is just a Struve global compactness type argument. This type of thing has been now in Schrödinger wave equation. This is like the Merle, Koenig-Merle approach. This is exactly the same thing. Well, okay, so initially I assume here, right, that I blow up, right? But I didn't prove that I blow up, right? I assume if I blow up, I'll blow up this way, okay? And so usually when you blow up for parabolic equations or like time dependent, you ask which type of blow up. So time 1, like which is self-similar fashion, type 1, sorry, or type 2. And actually Peter Topping proved that the blow up rates lambda I are of this form and this type 2 blow up. Okay, so you are in the situation which is hard. Okay, so this is basically the global picture, and the result that Chang, Dig, and Ye, and also more recently and more like complete of Davila, Del Pino, and Wei, constructed effectively blow-up solutions, right? And of course satisfying this scenario, right? by parabolic gluing. I will come back to that later.
So the domain is two-dimensional.
Yeah, yeah.
You can have a higher dimensional target.
Yeah. The domain, for what I'm discussing in these slides, like the dimension of the target don't matter. What is important is that it's smooth. If I'm on a singular space, which is another type of, then it's another better, yeah. Smoothness, compact, and whatever dimension. Okay. There are many places where you want the target to be hyperbolic. In GR, for example, you want the target to be hyperbolic.
So, I mean, is there a good analysis of, as you approach a singularity and you rescale near the singular points, you get sort of standard models of maps to spheres?
For which target? For the.
I think it's probably much easier if it's S2, but if you have a higher dimensional sphere.
Yeah, this is It's going to be It's going to be also sphere. It's going to be also spheres or even higher dimensional. This is going to be you will bubble always like an entire map, so map defining all R2 into your target. The problem is that what are these maps? When the target is a sphere, by analysis of this equation, 4, you can prove that they are rational functions. But if they are like, if n is another, like a more general target, you cannot classify them. And sometimes having that classification is very important, depending on what you want to do. But in general, this strategy, or this picture, I should say, is independent of the target.
Sorry. I see. What's the type 1 singularity? Here you just...
Type 1 means that it's a self-similar fashion. It keeps the scaling in a self-similar fashion. And I'm not type 1. Type 1 means that basically, if you take the ODE, well, here you cannot like this, but it's the ODE blow up. It's much easier to see when you look at this type of energy critical equation. Type 1, you solve the ODE, and you have U, which is given by something explicit, and type 2 is all the other ones. Okay, so I didn't discuss, because it's impossible, well, because there are too many results, so why harmonic maps are interesting. There are many good reasons for that in geometry, in topology, and I mean, like entire books written on that. Let me mention that this type of equation, which seems to be mathematically interesting, happens also, like occurs very, I should say, like naturally in some liquid crystal flows equations. Actually, so when you go back to physics, trying to describe the way crystals are to understand the dynamics inside the fluid of a crystal, basically, like if Eriksen and Leslie on one side and Landau and Dejean on the other side developed many models to understand this type of behavior of their material, and one of them is coupling two equations. One equation is the Navier-Stokes equation, is the first one, which is at the macroscopic level describing the way your fluid is moving, with the harmonic map equation. The harmonic map is capturing the orientation of the crystal, okay? Because the harmonic map here, this is an harmonic map to the sphere, so it's modulus 1, right? The orientation of the crystal would be on the sphere, right? And so basically, this model as written like this has been derived by Francois-Lee in the late 80s. It's not exactly, the model of the CCC is much more complicated than that. But this one is already enough complicated mathematically. And so basically it's coupling two things through a very special coupling. Like on one side you have Navier-Stokes, which is like the famous fluid equation. On the other side you have the harmonic map heat flow, and you have this coupling here, which involves only the harmonic map part, and this transport term on the heat flow of maps, right? So this is really like an idealized version of the original system of Eriksen and Leslie, which contains much more terms, and where all the energies are much more complicated. But this one is capturing even like when you use it for numerical experiments, the physicists really observed, I mean, it seems to be a pretty sensible problem. Okay, and so basically what Frank Walling studied is exactly what I described to now for this model, trying to understand the development of defects. What the physicists want to understand, as far as I understood, is how, like, your crystal is developing filaments or vortices, so point or filaments, like line defects. And if it develops a line defect, what is the dynamic under the flow of this defect? And all these type of questions, but it's mainly, they are not that interested into like proving that you have smooth solution. They want to see the really like the development of defects. And so basically, there have been several works culminating for this model, culminating with these two things recently. Is that first, in dimension, so you want us to imagine the following thing. In dimension 2, you couple Navier-Stokes in 2D with harmonic nematic flow in 2D. So Navier-Stokes part in 2D should be good. Navier-Stokes in 2D a priori is good. But the harmonic map part is blowing up. Well, the thing is that the coupling that you have acts as a singular forcing for Navier-Stokes. And as you know, if you have singular forcing even in 2D, this is a problem. So actually, they managed to prove in 2D some sort of partial regularity à la Caffarelli-Cohn-Nirenberg, but not exactly with the best singular set estimate. And in 3D, the situation becomes drastically more difficult, and actually they managed to prove the global existence of solutions under like additional assumption without any partial regularity statement. And the reason why they put the orientation field to be like only in the hemisphere is to avoid because you can prove that if the harmonic map flow, the target is only in a small geodesic ball, you don't develop singularities. So you want the singularities of your flow coming only from Navier-Stokes part, if there are some in 3D, okay? And finally, just recently, they managed, like Yannick Sire, Frank Walling, Shangyu Wang, Juncheng Wei, and Yifuzhou managed to construct finite time singularity solutions. Solutions of the liquid crystal flow blowing up in finite time, in 2D, one thing. Okay, I will come back to that. The good thing with this model is that of course, here you're accumulating issues. You're accumulating the issues coming from Navier-Stokes and the issues coming from the heat flow of harmonic maps. However, a lot of problems or a lot of systems of PDEs coming from physics or like are actually of the same type of structure. That where you have like an harmonic map flow coupled with some diffusion part. And,
so the kind of positive result you mentioned before, when this orientation vector remains in a hemisphere, and these singular ones, they presumably don't have that property. Is that?
No. The thing, no, they don't have that property.
So you have some good direction where you have some positivity. And
yes. This is, even in this situation, this is a very partial result. This is very hard. I mean, the harmonic, once again, I will come back to that. Like, this system is complicated, but shares a lot of similarities with other systems, so that's why. So up to now, what I described or tried to describe is actually development of singularities. Never, like, whenever my domain, okay, is without boundary. Okay, so what I did, this is what I started with, okay? I take,
Just a simple question, what does nematic mean? Like,
I think that this is the way the droplets are moving. I'm not sure even what nematic means in English. I'm not English, not my mother tongue, so I'm not sure that. I think that this is the way, the properties that the particles are having inside the crystal are having inside the flow. I'm not sure that, like, I should erase it because it's always called this way, but yeah. And yeah, it has a very specific definition, but now I forgot. Yeah, so basically up to now, everything I described could be done up to technicalities, assuming the domain is actually not a disk like I did, on which I put directly data, but a closed manifold without boundary. Okay, so that's why. So now what happens for boundaries? Okay. Well, of course, if I put a boundary, there is, again, I can use the boundary to put a directly data on it. But geometrically, directly data is not geometric. And even for Navier-Stokes, directly data is not that good. So there is a notion of harmonic maps. Oh, let me show you like some so these people here, these are pretty recent papers. Have been like, so they are interested in understanding. So these are like related to the rings of Saturn. And they want to understand how the rings are moving, right? And typically these are liquid crystal type and how all these defects are developing, like occurring and how they evolve under the flow. They are really like, I mean, all of these models are based on trying to detect defects, singularities. It's not that much that you want to prove regularity. And, okay, so what happens if the domain has boundaries? So there is a very natural notion of harmonic map, a geometric notion of harmonic map with like boundary, which is called harmonic map with free boundary. So it's a bad, I never understood why it's called with free boundary, because this is not a free boundary problem. But the idea, so the setup is a little bit more complicated. So I take two closed manifold M and N, like before, two compact manifold M and N, but M, the domain, has a boundary. And I say the following, well, let me take a submanifold sigma on the target, okay? So I have M, I have N, and let me take sigma, a submanifold in the domain, in the target, sorry. And let's solve the following thing. Well, if I take, so it's k-dimensional, it would be n, and it would be n if you want. And I put the constraint that my map maps the boundary into sigma. Okay. Okay. So I have m, let me write it this way. I have m, dm, should write it. So basically, like, if you take a continuous map from M to N, satisfying this constraint, right, it defines a relative homotopy class whenever you put the domain, the boundary of the domain. And you are like, so it's very natural this way to consider, like, to keep track of the boundary. But if you look at if you look at harmonic maps under this constraint, then you have this highly nonlinear problem, which is you have the harmonic map equation inside, you have your constraint, and the constraint gives you a Neumann nonlinear condition, very nonlinear condition, okay, particularly in high codimension. On sigma, right? And these harmonic maps are called harmonic maps with free boundary. But once again, what is a free boundary here? This is the image by U of dm, okay? But this is not a free boundary in the sense of free boundary. This is not that you are trying to solve an equation on a domain that you don't know. It's more of a constraint problem, right? So well, if you are thinking about harmonic maps in general as parametrizations of minimal surfaces, minimal immersion, it would give you parametrization of minimal surfaces with free boundaries. So imagine that you are in the ball, you have a minimal surface inside the ball, and you hit the ball orthogonally. Okay, so the free boundary condition, this is exactly what this is telling you, right? But the system becomes very nonlinear because not only you are nonlinear inside, right, but also on the boundary. So at the level at the PD level, there are two things that are interesting is, of course, the regularity. The interior regularity is not an issue. This is the same as the standard harmonic maps. Now you want to understand what happens at the boundary, interior regularity or not, up to the boundary. But now, since we have a Neumann boundary condition, if you look at a system like this, so evolution equation, then you might blow up on the boundary. Okay?
So if M is two-dimensional, so can we get the blow-up over it's in the interior of M?
Also on the boundary of M. You can have both blow up.
Okay.
You can, if you're on the disk, yeah, right?
Yeah.
You can construct solutions, which I will come to that, solution blowing up here and here. A Neumann condition in general doesn't prevent blow up. Directly, yes. Boundary blow up. Directly, yes, but not Neumann. But geometrically, this is always Neumann popping up. Never directly, as far as I know. So if you want to, as you were asking, if you want to implement the same strategy, let's look at the gradient flow of that, right? And this is a harmonic map heat flow with free boundary. And you can study it like, you're going to have the same type of picture, except that indeed now your spikes can happen on the boundary of your domain. You might have boundary blow up. Okay? Well, here this is just to mention that if you look at submanifold theory, there is like a very famous link between minimal submanifold into spheres and eigenvalues of the Laplacian. Well, so you have the same analogy between, the same link between minimal immersion with free boundary into the ball, for instance, and Steklov eigenvalues, right? So Steklov eigenvalues are like you are looking at the spectrum of the Dirichlet to Neumann map. And it's been used by Fraser and Shane recently, but well, this goes back to before. In any case, if you open the books on minimal surfaces, like you will have always a chapter on minimal surfaces with free boundary. So let me come to
If okay, now we consider a two-dimensional case, and we give initial data with the finite energy. Can you control the how many points of the block points?
Yeah.
Okay.
Yeah.
So what happened? The block at the boundary.
I will come to that. In 2 seconds. So the picture for this heat flow is the same type. Okay, waving hands, right? And let me describe more precisely what happens at the boundary blow-up. Well, to do that, let's look, because you need to have like a model in the whole space. You need to understand entire harmonic maps, right? So it's related to a question that I will come back later. Like Chen and Lin, like in the 90s, studied like the heat flow of harmonic free boundary and tried to ask the question, is there a non-trivial blow-up solution? In exactly the same way Chang, Dig, and Ye proved the blow-up solution for the classical harmonic map flow. The thing is that the classical harmonic map flow in some equivariant classes reduces to a nice system for which you can build barriers and so on. It happens that this flow of harmonic map with free boundary is highly non-local and highly non-linear. So one has to use other techniques, and the techniques in particular built on barriers are not working to construct blow-up solutions. And this is what I want to discuss now, like the high non-locality of the flow. So let's take a very simple model. Let's take that sigma, my constraint, is S1. Let's take the domain to be the half plane. And then if you write down the equation, it becomes like you have the following thing. You have the half plane, and you solve the equation, the heat equation inside. You cannot deny, sir. You have this kind of funky boundary condition, right? Orthogonal, which is a non-local one, right? On the boundary. And you try to, and you have, of course, your constraint that the boundary of the half plane, right, has to, right? This is the thing that you want to solve, okay? So it's possible to construct weak solutions of that, which are partially regular. And let's look at first at stationary solution. So, okay, so it satisfies this model. Well, but actually what you can prove is that if you take V to be the restriction of U on the boundary, okay? So you take the trace U, you take a solution of this thing, and you look at V to be the trace of U here. Well, you can prove that V satisfies this equation. Okay, this is not obvious, but this is because sigma delta 1/2 is exactly the directly to Neumann map, right, of the harmonic extension, right? And so basically when you use the symbol that it has to satisfy, you check that V satisfies exactly this equation in 1D. But it happened that this equation had been introduced for another purpose before by Dalio and Rivière a few years ago. And you can prove that any weak solution of that is actually C alpha. And the thing is that if you look deeply at, I mean, if you look like a little bit at the equation, this is an harmonic map type equation, but not for the Dirichlet energy, for the H1/2 energy. Okay? Exactly. Let me, oops. Not for the Dirichlet, for the for the H1/2 energy. So this slide is just telling you the following. If I have an harmonic map with free boundary, and I take its restriction on the boundary, I build a new map, which is now, for which like, I don't have a boundary, right? I'm on the boundary itself, which satisfies an harmonic map type equation, in particular, which is invariant under some symmetry group, and which actually you can use, you can study by many techniques developed recently, and these maps are called half harmonic maps. Okay? But now if I give you a half harmonic map, a solution of that, and I convolve with a Poisson kernel, I build a harmonic map with free boundary. By the very, so now I have a way, this small remark, it may, like, tells you that, well, okay, if I have this very nonlinear problem, somehow, I have a way to understand the boundary regularity by just restricting and developing a theory on the boundary, because I can reinterpret my Dirichlet to Neumann map operator as a nice integral differential operator.
Is that the last equation on this slide is supposed to say parallel rather than perpendicular? Because you would be leaving the target sphere otherwise. It must be projection into the tangent space, right? Not perpendicular to it.
Yeah.
Parallel, not perpendicular.
Yeah, parallel. Yeah, sorry, yeah. And so basically, yeah, definitely. And so basically, like, there are, so this type of analogy is very useful, and I mentioned before this analogy between, I mean, not this analogy, this dictionary between going on from the boundary, taking the harmonic extension, or having the harmonic extension and taking a trace, is very useful, and this is the way we actually solved, we built blow-up solutions for this problem that I was mentioning. Let me come back to that in 1 second. So there are examples of half harmonic maps, okay? For example, the stereographic projection from R into S1 is an harmonic map, okay? It's a half harmonic map. You need to check it, but, there are examples, okay? And actually we classified them more or less for S1. And what we did with Junshan Wei and Junshan Zheng a few years ago is that we answer positively the question of Frank Wally in the sense and United Chain when we consider like this problem, right? And with the following data, let me take k points on the boundary. Well, inside nothing can happen. You are like this is caloric, right? Inside, I mean, you can be as you cannot have blow up inside. So, because it just solves the heat equation. So let's take k different points, right, on the boundary. Then I can find the time capital T and an initial data, U0, which is nice actually, such that when I get closer and closer to this capital time T, I have this type of asymptotic limit. So I observe that I have a body map, which is stationary, and I will develop k bubbles at each of the k points, right? And all these bubbles are entire half harmonic maps which I extend harmonically. Okay? And the blow-up rate, lambda I, is this kind of funky thing, right? So the way we did that is by gluing, so it's a bit technical, but the idea is that really like the gluing that you do in geometry, like you want to glue two things but in a parabolic fashion, in the sense that it's a parabolic version of the gluing where, I mean, a lot of similarities. And the thing is that it works for parabolic equation very well. I will come back to that maybe, like because parabolic equations are regularizing. If I was trying to do this type of construction on Schrödinger equation or wave equation, I'm doomed because I don't regularize, of course. But let me mention though that it's not, I mean, there is another flow that I could consider, which is the bad flow between quotes mathematically, because it's, so this is a flow that, this is a direct gradient flow of half harmonic maps, right? So now I look at this one. So in other words, looking at this extended version, now I'm harmonic inside with a dynamical boundary condition, right? The stationary solution of this and this are exactly the same, right? If I kill dtu, right, they are exactly the same, okay? But these two flows are different, right? They are not the same gradient flow. And actually, like for many reasons, this is a bad flow, but recently, actually, not like a few years ago, Struve released a very nice paper where he proved that actually it's a very good flow for Plateau problem. It's a way to flow to obtain solutions to the Plateau problem. So it's very good for Plateau conditions. So it's a bad flow because I cannot prove some, by monotonicity here I always assume much stronger monotonicity than just decrease of energy. And these are like quantities that I want to be able to study the flow, like a partial regularity in particular. So basically, like the interesting thing of this analogy is that this functional here, okay, is actually the functional which is associated to half harmonic maps, right? And this functional is also invariant in one dimension under the Mobius group, okay, by traces of conformal maps keeping the half plane invariant. And the reason why Dalliot and Rivière introduced this functional is that they wanted to exhibit compensated compactness in odd dimension. Like all of the things, all the regularity of this equation here is based on the fact that in 2D it's conformally invariant. That's why you have full regularity. But the equation in 3D becomes super critical, okay? You lose this conformal invariant. Is there a system which is conformally invariant in dimension 1? Well, this is this one. And that's why they call it half harmonic maps. But it happened that we figure with Vincent Millot after that these half harmonic maps were just a reformulation of harmonic map with free boundary. And because of the tool which has been recently developed for integral differential equation, we could actually like thinking about this result. This result is reformulate. This result is based on the fact that this equation, this problem here, can be reformulated this way, or like project to the 10. And V is a trace in space of it. So it's a kind of funny equation with the square root of the heat operator and not the half and not the Cauchy operator. Well, anyway. So the thing is that so why, the only point that I'm making here is that there is a way to study this boundary value, not very nonlinear boundary value problem by just looking at things which are defined on the boundary and using tools that have been developed intrinsically for integral differential equation. This is the point that I want to make. So, and I will explain why later. But then actually recently with Frank Hualin and Jun Sheng Wei and Yifu Zhou, we introduced a model of free boundary for these liquid crystals. And it happens, a very, very funny thing happening is that these conditions, so these two conditions here are like the free boundary conditions that I developed before. But what do you have to take for Navier? Well, it happens that the natural Navier conditions are actually the correct one to have dissipation of the energy. Okay? Because you could have, if you put a free boundary on the domain, you could take several several boundary conditions for Navier-Stokes. It happened that the very natural one coming with dissipation as a Navier one. So they are a little bit complicated because this S is, how is this called? The strain tensor, right? Or deformation tensor. But actually, it comes really naturally when you compute energy estimate and you try to build quantities which are decreasing in time. This is really what you need to make all the boundary integral vanishing, right? And it happened that we managed also in this case to prove blow up and exactly to come back to the question that you asked me about boundary blow up. What we did is that now I pick points on the boundary, points inside, and I construct finitely many, and I construct blow-up solution at each of these points. Except that depending if I'm inside on the boundary, I have to put a different bubble because they are not the same global models, right? Here I have a true harmonic map, here I have a half harmonic map. A true harmonic map comes with mass 8 pi, right? This is a direct computation. A half harmonic map comes with mass 4 pi, okay? But you can still construct a solution of this system, not liquid crystal system with free boundary, where all the blow-up points are on the boundary, all of them are inside or both. Okay, except that so you have this decomposition in exactly the same way. And except that you are paying a different price for the concentration of energy, right? A half harmonic map comes with energy at 4 pi, and standard harmonic map comes, standard bubble in S2 for energy 8 pi. Okay? So let me finish by, so one can prove, this is a recent, one of my students, one can prove that this liquid crystal flow with free boundary in 2 dimensions has global, partially smooth, weak solutions. in a quite general setting. Actually, one can understand also like what is the asymptotic behavior, but the result in 3 dimensions is completely open. Okay, I don't know how to, well, it's pretty hard. So let me mention that just to sum up, what I try to kind of explain. First is that in the construction of these blow-up solutions, so it's a construction which is pretty explicit, I should say. And so we use like this type of parabolic gluing, where basically you are like just, this is really like a rigorous version of the matching process, that you have like a region with high concentration, you plug a bubble there, and outside of this region you are nice, okay, and you match the two. So you are really gluing that exactly you do, I mean your picture in geometry, doing connected sums, for example. And then the thing is that it's much more involved because like you have all this parabolic thing to take care of, and to match the different regions, but actually for all these critical problems and many others, it works pretty well. It doesn't work well for supercritical, of course, but for all these critical models, I mean, several of them, right, it works well. As I mentioned, like why I got interested into this liquid crystal flow, because like actually the structure of the system is shared by many other PDEs. One that I like a lot, which is a flow introduced by Topping and Rupflin on how to produce minimal immersion, branch minimal immersion out of any surface. So you run the harmonic map heat flow, but you allow the metric on the domain to change, and you run the metric along some actually curve in the Teichmüller space, because along the geometric, the metric is varying like basically the Hopf differential, like projection on the Hopf differential. So it's basically telling you that whenever I have a stationary solution, it has to be Hopf differential 0 and harmonic, which means that conformal and harmonic, which means minimal. So this is a very, and this Teichmüller flow of Topping and Rupflin shares a lot of properties of liquid crystal. It's easier, but, and you can make a lot of variations of it. And the last thing that I would like to mention, and this is because I've been always wondering why all these rigidity results were that can be discussed in geometry or in topology have been done for manifold without boundary. And when I was asking some colleagues in geometry, they were asking me, we don't know what to do with the boundary term if we do use Bochner type arguments. But like the thing is that now with this approach somehow, like it helps to understand better the boundary terms, at least the regularity, which is pretty important when you have like general settings. And also, if you leave the boundary free in the way that I mentioned, it seems to me that one should be able at least to give some rigidity result whenever you take a manifold with boundary, for instance, at least for some type of problems. And I think that I should stop now. Thank you very much.
Could you say more about the formation of singularities in these problems on the level of, like, if you zoom in, what can be proved?
The flow?
Harmonic flow.
Yeah. Like this, if you zoom in, this is exactly, you see exactly. Okay, so one has to, okay, so at this level, if you zoom in, this is what you see at the singularity. You see a bubble. You're gonna see, you're gonna like translate, like scale and dilate this bubble, scale actually. An entire harmonic map from S2, let's say, into S3. Okay, this is your target, or S2.
Inversion at some point.
This is the picture. When you zoom in here, this is the picture you see. Like you really see only that. Now, is it the best way to understand the flow? Well, it's a way to understand the singularity formation. Then you could ask the following thing. Let me take, which is I think more challenging but more interesting. Let me take any kind of approximation of my flow, Ginzburg-Landau. Okay? Let's penalize the constraint. Let's build like a smooth flow, and let's look at limits u epsilon goes to u. So in a kind of natural sense, you're going to build out of this penalization a solution of your harmonic map heat flow. But the thing is that what is more interesting to look at is the way the parabolic measure, defect measure are evolving. With a flow, right, you develop, because of this analysis, you have always a defect measure, which is the one contributing to the singularity, right? The thing is that you could look at an approximation of the way the densities of energy in space and time are evolving under the limit epsilon goes to 0. And this, by some pretty difficult result of Wang, like Lin and Wang, you can prove that these tangent flows, they are called tangent flows, so this limit of flows in space and time, what you are seeing are either the bubble or self-similar solution of the heat equation. So actually the picture is even more complicated than that, because this is giving you only part of the picture. It's giving you what you see like in the, how can I say, like what you see like the physical space, right? But if you look at the way space-time, right, concentrate in the limit, you see also self-similar solution of the heat equation. So the contribution to the parabolic defect measure, like, are coming also from other objects that you need if you want to pass the flow that you need to rule out one way or another in general.
So yeah, we know the harmonic map corresponds to a branch linear surface, right? So is there a relation between the harmonic heat flow and mean curvature flow?
Not that I'm aware of. The way, not that I'm aware of. Oh no, yes, there is. Okay, so there is something that I've been always kind of puzzling me. Is that take a harmonic map heat flow and take a space-time point in the singular set of your flow, okay? So let's imagine that you are in higher dimension. You have a line, this is your singular set in space and time, and you take a point there and you blow up in the sense of rescaling, okay? What you see is a brachyflow. So it's a weak mean curvature flow. So it's a paper by, I think, Jiayuli and Yang Qian many years ago. And then they had like a constant which was not, it was a variation of the brachyflow, and actually Shang-Yu Wang and Frank Wan proved that no, this is a brachyflow. So if you blow up a singular point of the harmonic map heat flow, you build a brachyflow. So weak geometric flow. And this is due to the fact that you can pass to the limit somehow in some energy inequality, local energy inequality of the heat flow. If you can use somehow the problem is that, I mean, at least from how I see it, this is not a curvature flow. It's really a parametrization. So indeed, like, you might think, okay, it could be used maybe to study some approximation maybe of mean curvature flow. But actually, like, the only effective approximation of the mean curvature flow I know is Allen Kahn, right? So that's why, like, I don't know if harmonic maps will, it's a system, so it will help you. However, of course, there are many similar. I discussed just one case. I mean, you could consider like targets to be hyperbolic spaces, non-compact. I mean, there are plenty of things that you could do, and harmonic map with infinite energy, which are very important if you want to prove. The way like you prove rigidity is using these harmonic maps. I mean, one way to prove rigidity, I guess, using these harmonic maps.
So if I understood correctly, in this discussion, you did consider varying the metric on the domain, but not in a way that depends on time. To stand any chance of getting a flow to a minimal surface or something like that, you'd have to try to arrange for the map to become a conformal map.
Yes, yes. This is what Röpfling and Topping have been doing in the case of minimal surfaces. They managed to rearrange so that, like, in some limit, up to a sequence of time, right, you bubble like a branch minimal immersion. And the way you do that, this is because you manage to couple to your harmonic map heat flow on the surface, the metric, change it like at every time along some trajectory on the Teichner space. And that's why they could also develop like Sachs-Uhlenbeck bubbling theory in higher genus, which was, I think, like one of the nice features of this. And this is a very natural flow. This is really like, but for example, you can, I think that in string theory, there are versions of where you have the harmonic Ricci flow, because you could take an harmonic map and changing the metric on the boundary along on the domain, with respect to any curvature flow that you want. And actually, I think that, for example, in theoretical physics, like there are models where you couple Ricci flow for the metric G with harmonic maps. And the coupling actually is extremely similar to the very similar to the coupling of liquid crystals, because if you look deeply, this is just the Hopf differential. Well, just the components of the Hopf differential. So actually behind this Ericsson, so this is called the Ericsson-Leslie tensor. It's trace-free, and this is basically, you are copying here the Hopf differential. So this type of thing appears very often in a lot of models. In particular, this Teichmüller flow, but
Okay, there are no other questions.
Thanks.